Hello students, today we are starting with a new chapter in SOM. The name of the chapter is strain energy. So let us start with this chapter. We are starting with this new topic. Now let us understand what is strain energy. Strain energy is the energy which is stored in any material when it is loaded. It means when we are loading, we are applying a load on a material, that material will get deformed, and because of that deformation there is some energy stored in that material, and the moment we remove the load, that material would be releasing its internal energy. It means, here I will write the definition of strain energy. Strain energy is the internal energy which is stored in any material which is loaded within its elastic limit. So here is the basic definition, the most simple definition of strain energy, that it is defined as the internal energy which is stored in any material which is loaded within its elastic limit. It means the condition for strain energy is that the material should be loaded within elastic limit. It should not go into permanent deformation, that the material will be deformed only temporarily, it will store the energy, and the moment we are removing the load, the material will release the energy. So that is the concept of strain energy. Now, strain energy is also called as the work done by a loaded material. So here strain energy, we can also say that it is the work done by a loaded material. Next, it is also called as resilience. The other name for strain energy is resilience. And since we are talking about energy, the unit of strain energy is either it will be in terms of Newton meter or Newton centimeter, Newton mm, or kilonewton meter, kilonewton centimeter, or kilonewton mm. Since it is energy, so here we have load into displacement. And next, for strain energy to be stored, material must deform within elastic limit. That is, for strain energy to take place, material should change its shape, and the change of shape should be within elastic limit. That is, it should not get permanently deformed. Next point, strain energy depends upon applied load. The amount of strain energy stored in any material depends upon the load which is applied. This applied load, it can be gradually applied load, it can be suddenly applied load, or it can be impact load, that is a load which is falling from a height. Now As far as application is concerned, strain energy principle is used in springs. As we all know, springs are elastic members. When we are applying load, spring will get deformed, and when the load is removed, the spring will regain its original shape. So you can treat a spring as a material which has strain energy, or you can say stored energy, because the other name for strain energy is the internal energy, or you can say the stored energy. So as we know, spring, when we are applying load, it will change its shape. This change in shape is called a strain, and because of that, whatever work is stored inside the spring, that would be called as strain energy. Next, when the load is removed, material will regain its original shape. Next, the load applied on a material can be, we have three different cases in which the load can be applied. The first one is gradually applied load. Next, suddenly applied load. And at last, we have impact loads. Impact loads are also called as load falling from a height. So we see that there are three methods or three ways in which load will be applied on a machine member, or you can say any material, and the load is gradually applied. Gradually applied means the load will be in the form of steps. Suddenly applied load, the total value of load would be acting together on a member. In impact load, the load will fall from a height. So in all these three cases, the strain energy value will be different, because as we know that strain energy, the stored energy which is there inside a material, it depends on the type of loading. Next, if we say that it is resilience, means strain energy is the resilience, then you can say that resilience is the energy which is stored within elastic limit. It is given by letter capital U, means we will be denoting resilience or strain energy by letter U. Next, I will give you the formula of strain energy. Strain energy, it is given by the formula U is equal to sigma square upon 2E multiplied by volume. So here I have written the formula for strain energy. So here we have written the formula for strain energy, where I can say that sigma, it indicates stress in the material, unit will be Newton per mm square. Capital E is the Young's modulus of material, and V is the volume of the material. And strain energy unit it will be Newton mm if I put these values. Now after this I'll write how this formula has come. I'll say that strain energy in an axially loaded member. So how the strain energy formula is developed? Here if I consider a bar or a rod which is loaded axially, and I will consider the load as tensile. So here I can see that the stress which is stored in the bar, that is sigma is equal to P upon A, and this stress which is stored, I'll call this as, from this stress, because of this there will be strain energy, which I will denote it by letter capital U. Now when this member is loaded, we will be getting the behavior of this rod, and I'll plot it on a graph. On y-axis we would be having load, that is P, load. On x-axis we would be having the deflection. Deflection is delta L. Now the graph would be linear since I am considering the load to be gradual. So here I can say that I am getting this area, shaded area, because when you go on increasing the load, deflection will go on increasing. This is gradual load. Now from this I can say that area under the curve will give me the energy stored. So I'll say that area is equal to half into P into delta L, that is the area of this right angle triangle. Now since we know that stress is equal to load upon area, so therefore load is equal to stress into area, so this formula will be half into stress into area into delta L. We know that delta L, deflection, is equal to PL upon AE. So P upon A is equal to stress, so it is equal to stress into L upon E, stress into L upon E. So therefore here I have this as equal to sigma square upon 2E. A into L will give me the volume. So here I am getting two conditions. From the first condition, I am considering that a member is subjected to external load. Because of this there will be internal stress, and because of that internal stress there will be strain energy stored. I give that value as U. Next, the same behavior if I plot it on a graph, I am getting the area as sigma square upon 2E into V. This area is nothing but strain energy which is stored. So if I give U as equation 1 and sigma square 2E upon sigma square 2E into V as equation 2, so from 1 and 2 I will be getting the same formula, that is sigma square 2E into V. So this is how the formula of strain energy is developed. Now after this I'll write down what is proof resilience. Proof resilience, it is the maximum strain energy stored in a material. So in other words, proof resilience becomes maximum strain energy. and we can say that maximum strain energy will be given by, it is U max, which will be equal to sigma max square upon 2E into volume. So this is the formula for maximum strain energy. After this, I'll write another definition that is called as modulus of resilience. Modulus of resilience, it is defined as the strain energy per unit volume. Mathematically, it will be denoted by modulus of resilience is equal to, it is equal to strain energy per unit volume. We know that strain energy is sigma square upon 2E into V, and here we are dividing by volume. So the formula which I have of modulus of resilience, therefore I'll say mod of resilience, that will be equal to just sigma square upon 2E. So here I have written the definition of Prof resilience and modulus of resilience. Now, since we know the strain energy formula, let me write three different formula of stresses for three different cases. It means the heading is stresses in members for different cases. Here I will first write down the first case is gradually applied load. As we know that strain energy depends on the method by which we are applying the load. So first we are seeing gradually applied load. So for gradually applied load, stress is given by sigma is equal to P upon A in Newton per mm square. Next, for suddenly applied load, stress is given by sigma is equal to 2P upon A. And the last case we have, that is for impact loads, that is load which is falling from a height. So for that, stress is given by sigma is equal to P upon A plus square root of P upon A whole square plus 2 EPH upon AL. So here I have the formula for impact load. For gradually applied load, we have stress as load upon area. We can illustrate this with a diagram. So here is the example of gradually applied load, where the moment load goes on increasing, you can say deflection will be increasing. Here I have shown area, actually this is deflection. So the graph is between load versus deflection, and the moment you go on increasing the load, deflection will go on increasing. That is for gradually applied load. Next, for suddenly applied load, here as the load increases from 0 to a value suddenly, there is increase in deflection. So here we have the diagram for suddenly applied load. Next, for impact load, I'll draw the diagram on the next page. I will say that for impact loads, or impact loading For studying impact load, here we have a diagram in which there is a rod and one end of the rod is fixed. To the other end we are attaching a collar. Now over this rod there is a weight which is placed. I will denote it by P. This P is at a distance of H from the collar, and the moment we are releasing this load, this weight will try to strike the collar and it will try to pull it. So because of this, there is change in shape of the rod and strain energy will be stored in the rod. So here I will write the formula of strain energy as I have already written previously also. So strain energy for impact load, U, it will be equal to sigma square upon 2E multiplied by volume, and here stress for impact load is given by P upon A plus square root of P upon A whole square plus 2 EPH upon AL. So here is the formula to calculate stress for impact loads. Once we know the value of load which is falling from a height, we know the area of the rod, Young's modulus for rod material, H is the height between the weight and the collar, area of the rod and length of this rod, then we can easily calculate the value of stress, and once this value of stress is known, we can put it in the formula of strain energy and get the answer of energy which is stored in this rod. So like these concepts would be there in strain energy, and once we finish off the concepts we can easily start with the problems.